When two objects collide, a lot can happen in a very short time. One object may slow down, the other may speed up, or they may even stick together and move as one object after the collision. In this video, we will focus on collision in one dimension. That means all the motion is along a single straight line. So we can use positive and negative signs to represent direction. The key idea is that total momentum is conserved during a collision if the objects form an isolated system. But kinetic energy may or may not be conserved. That difference is what separates elastic collisions from inelastic collisions. We will first compare elastic and inelastic collisions and then solve an example involving a hockey puck caught by a goalie. Let us begin with the basic condition for using momentum conservation in a collision. The total linear momentum is conserved when two objects collide, provided the two objects make up an isolated system. In practical terms, isolated means the net external force on the system is zero or small enough to ignore during the short collision time. During the collision, the objects exert forces on each other. Those are internal forces if both objects are included in the system. Internal forces can change the momentum of each individual object, but they do not change the total momentum of the system. The small diagrams on the slide show different kind of collisions. The objects can bounce apart, lose some kinetic energy, or stick together. But if external forces are negligible, the total momentum before the collision equals the total momentum after the collision. This does not mean the total kinetic energy is always the same. Momentum is conserved for all isolated collisions. Kinetic energy is conserved only for a special type of collision called an elastic collision. Now let us define the first collision type, elastic collisions. An elastic collision is a collision in which the internal kinetic energy of the system is conserved. Internal kinetic energy means the total kinetic energy of the objects inside the system. For two objects, it is the kinetic energy of object 1 plus the kinetic energy of object 2. In an elastic collision, two things are conserved. First, total momentum is conserved. In words, total momentum before equals total momentum after. Second, total kinetic energy is also conserved. In words, total kinetic energy before equals total kinetic energy after. The diagram shows two blocks on a frictionless surface. Because the surface is frictionless, we can treat the two block system as isolated in the horizontal direction. During the collision, the blocks push on each other, but those forces are internal to the system. A useful example of an approximately elastic collision is two hard objects bouncing off each other with very little energy lost to sound, heat, or deformation. In the real world, perfectly elastic collisions are idealizations, but they are very useful models. Next, let us compare this with inelastic collisions where kinetic energy is not conserved. In an inelastic collision, total momentum is conserved if the system is isolated, but internal kinetic energy is not conserved. This means some of the initial kinetic energy is transformed into other forms, such as thermal energy, sound, or deformation of the objects. The slide shows a special case called a perfectly inelastic collision. Two objects of equal mass move toward each other with equal speeds. They stick together after the collision. Since their momenta are equal in magnitude and opposite in direction, the total initial momentum is zero. After they stick, the final velocity is also zero. Momentum is conserved, but kinetic energy is lost. Before the collision, both objects were moving, so the system had kinetic energy. After they stick together and stop, the kinetic energy is zero. That missing kinetic energy was transformed into other forms during the collision. The phrase perfectly inelastic means the objects stick together after the collision. That is different from regular inelastic collision, where objects may not stick together but kinetic energy is still not conserved. Now let us apply these ideas to a hockey puck that is caught by a goalie. In this example, a 70-kilogram ice hockey goalie is originally at rest. A 0.15 kilogram hockey puck is slapped toward the goalie at 35 meters per second and the goalie catches the puck. Part A asks for the recoil velocity of the goalie after catching the puck. Since the puck and goalie move together after the catch, this is perfectly inelastic collision. Part B asks how much kinetic energy is lost during the collision. This reminds us that momentum is conserved, but kinetic energy is not conserved in this collision. We assume friction between the ice and the puck goalie system is negligible. That means there is no significant external horizontal force during the short collision. So we can use conservation of momentum. Before calculating, let us make a prediction. The puck is moving very fast, but its mass is tiny compared with the goalie. After the goalie catches it, the combined puck goalie system should move forward but very slowly. Now let us calculate the recoil velocity and the kinetic energy lost. Let's first write down the given values. Mass of the puck is 0.15 kilograms and the velocity of the puck is 35 meters per second and the mass of the goalie M2 is 70 kilograms and the initial velocity of the goalie is 0. For part A, we can use the conservation of momentum. So the total momentum of the system at the beginning is m1v1 plus m2v2 and that is equals to the total momentum after, let's say, m1 plus m2 times v final. Since both objects are moving together, we only have one final velocity. Now, the initial velocity of the goalie is 0, so this part is 0. So our equation becomes m1 v1 equals m1 plus m2 times v final. So we can rearrange this to find v final. So v final is equals to m1 v1 divided by m1 plus m2. Now we can substitute the values. So m1 is 0.15 kilograms times v1 is 35 meters per second divided by m1 plus m2 0.15 kilograms plus 70 kilograms and we get the final answer 7.48 times 10 to the power minus 2 meters per second. So the final velocity is 0.0748 meters per second. This is a very small forward speed, which matches our prediction because the goalie is much more massive than the puck. For part B, we compare kinetic energy before and after. The kinetic energy before is equals to half m1 v1 square plus half m2 v2 square, and since v2 is 0, this part is 0 and the final kinetic energy is given by half times m1 plus m2 times v final square, and then to find the change in kinetic energy we can write Ke final minus Ke initial. So this is equals to half m1 plus m2 v final square minus half m1 v1 square. And we can substitute the values. So half times m1 is 0.15 kilograms plus m2 is 70 kilograms. m2 is 70 kilograms times v final 0.0748 meters per second, and that is squared, minus half times m1 is 0.15 kilograms, v1 which is 35 meters per second, and that is squared. So this is equals to 0.196 joules minus 91.9 joules, and we get negative 91.7 joules. The negative sign means the system lost kinetic energy. So the amount of kinetic energy lost is 91.7 joules. That energy was transformed into other forms such as thermal energy, sound, and deformation during the catch. The main lesson is that in a perfectly inelastic collision, momentum is conserved if the system is isolated, but kinetic energy decreases. Conservation of momentum tells us the final velocity. The kinetic energy comparison tells us how much mechanical energy was transformed.